Hi everyone. In the previous lectures, we introduced the idea of negative feedback amplifiers. We said negative feedback amplifiers offer two major advantages. One is a near constant DC gain, and the other advantage is reduction in nonlinear distortion. We said that if you can design an attenuation network beta, which is independent of temperature, process, and time, which means it doesn't drift with time, then in theory, using a high gain amplifier with a gain A and meeting this condition A beta much greater than 1, we can build an amplifier with a near constant DC gain given by 1 by beta. So to build that, you need this fixed beta. Only then you can build a fixed gain negative feedback amplifier. And we saw how the engineers who were working on these amplifiers in the early 1900s came up with this idea, and we saw the benefits that these amplifiers offer. Now we are going to look at other benefit other than these two, which the engineers thought that negative feedback amplifiers were offering them when they were designing it in the early 1940s. Now, as I discussed about negative feedback amplifiers, I said you have to meet this condition, which means A beta has to be much greater than 1, which means A has to be a really large number. To do that, the engineers were cascading several vacuum tube amplifiers to get a large gain. And they had to introduce coupling capacitors in between the intermediate stages of these amplifiers. And these coupling capacitors were starting to load these amplifiers, and they were reducing the bandwidth. They were facing two problems. They were thinking, one major issue was to make this negative feedback amplifier work. So they were constantly seeing these amplifiers becoming unstable, the negative feedback amplifiers. Now, to understand the frequency of negative feedback amplifiers, we will, by considering many or a large number of poles or a generalized frequency response of negative feedback amplifiers, we will understand that at a later stage in this lecture series. But right now, I'll try to explain one very important observation the engineers made at that time was that they were expecting, since the bandwidth was decreasing because of the loading of these coupling capacitors, the bandwidth of the amplifier should decrease. But instead, what they were observing in negative feedback, once they put these amplifiers in negative feedback, is that the bandwidth was increasing. So to understand how is that happening, we will assume a very simple mathematical model for the amplifier, which is a simple DC gain and a single pole. DC gain is A0 and the pole is at omega p. And A of S is the transfer function of this amplifier given by this expression. Now first I'll explain how does this bandwidth expansion happen, and then we will see, is this really a benefit of negative feedback amplifiers. So first we'll write the closed loop expression, the closed loop gain of this amplifier, which is given by A of S by 1 plus beta into A of S. So I have substituted A of S by A0 by 1 plus S by omega p in this expression. And I'm going to give the final expression. The DC gain will be A0 by 1 plus A0 beta, which is expected. We have derived this in the previous lecture as well. And we said if A0 into beta is much greater than 1, then we get the gain approximately equal to 1 by beta. The interesting thing to note here is that even after negative feedback, it still behaves like a single pole system. And the pole location now is at omega p into 1 plus A0 beta. So this is what the engineers refer to as an increase in the bandwidth or bandwidth expansion due to negative feedback. It looks like the bandwidth is increasing by a factor of 1 plus A0 beta. So what happened to closed loop gain? It is reduced by 1 plus A0 beta, and that's the consequence of negative feedback. But what we are noticing here is that the bandwidth has increased by a factor of 1 plus A0 beta. When we speak of single pole systems, we also introduce another important term called gain into bandwidth product. It's the product of DC gain times the bandwidth, 3 dB bandwidth for a single pole system. The 3 dB bandwidth is equal to the first pole itself. And we'll see what happens to this gain bandwidth product in case of a closed loop amplifier. So that is ACL into omega CL. Now we just saw that ACL becomes ACL is nothing but open loop gain divided by 1 plus A naught beta. So A naught by 1 plus A naught beta, and the pole, the closed loop pole, is omega p into 1 plus A naught beta, so that the product is simply the same as the gain bandwidth product of an open loop amplifier, which is A naught into omega p. So what we observe here is that the gain bandwidth product remains the same. Now what I have shown here is a Bode diagram of the frequency response of a closed loop amplifier and closed loop and open loop amplifiers. The first graph in yellow, we show the frequency response of an open loop amplifier with a DC gain A naught and a pole at omega p. The gain rolls off after that with a slope of minus 20 decibels per decade. Shown in red here is the frequency response of a negative feedback amplifier, and we can see that the gain remains constant for a larger range of frequencies. The pole here is at omega p into 1 plus A naught beta. So therefore, we can say that the bandwidth of this amplifier is increased by a factor of 1 plus A naught beta. Now the natural question one should think of is that, so which means, should I go for negative feedback amplifiers if I want to increase the bandwidth of an amplifier? Now to answer that question, you have to look at carefully what's happening in a negative feedback amplifier. Are we getting this increase in a bandwidth at the expense of something? And we can readily see that what's happening is that, of course, the bandwidth is increasing by a factor of 1 plus A naught beta, but the DC gain is decreasing by the same factor. So it looks like I'm trading off gain for bandwidth, such that the product of gain into bandwidth is same. Now this is a principle which engineers were already aware of. They knew that if you have an amplifier, you can reduce its gain and extend its bandwidth. To illustrate that, I've shown here a simple common source amplifier with a resistive load. We'll assume R0 is infinity. The DC gain will be minus of Gm times R, and the pole here will be 1 by Rc, and the transfer function is given by this. So minus of Gm R by 1 plus SRC. So DC gain here is GMR, pole is 1 by Rc. Now let's say I reduce my resistance by a factor X. So your DC gain becomes A0 by X, because your resistor reduces, DC gain also reduces. But the pole increases by the same factor. So this way, I was able to reduce the DC gain and extend the bandwidth. So this can be readily accomplished in an open loop amplifier itself. You don't necessarily have to go for negative feedback to get this benefit. The product of gain to bandwidth is given by Gm by C. Now, you should understand that I have increased the bandwidth of this amplifier without increasing the bias current. So again, this is something we'll talk about in detail when we discuss the CMOS op-amp designs. The gain into bandwidth product here is independent of the resistive load, and it depends upon the ratio of Gm by C. For a given bias current and load capacitance C, and when I say bias current and load, I'm assuming the device dimensions are all fixed, then the gain into bandwidth product is fixed. So which means I can keep varying R and varying the gain and bandwidth such that the product always remains the same. So this was something engineers were already aware of. So that's what I've shown here. In red here is the nominal amplifier gain given by GMR. By increasing the resistance, I could increase the DC gain, but the pole decreases. Similarly, shown here in green is that I have reduced R. And I was able to extend the bandwidth by the same factor by which the DC gain has reduced, so that the gain into bandwidth product remains more or less the same. So that's what we were trying to explain in this lecture. What we are trying to say is that it looks like negative feedback amplifiers helps in extending the bandwidth, but it is coming at an expense. It is coming at the expense of the DC gain. And what we are trying to explain here is that to get that benefit, one doesn't have to necessarily go for negative feedback amplifiers. You can get that gain bandwidth trade-off even in an open loop amplifier as well. But of course, you need negative feedback amplifiers to get the first two benefits, which is a gain which is independent of process, temperature, and which doesn't have undergo any time drifts. And the second major advantage is reduction in nonlinear distortion. Those two are the real benefits of negative feedback amplifiers. The bandwidth extension, though it looks like a benefit, it's coming at an expense of DC gain. So you don't really have to go for negative feedback amplifiers to get that benefit. Now we'll look at intuitively, or rather I'll probably further explain this gain bandwidth product example using the well-known amplifiers which we have already analyzed. So this is a common source, a common drain, and a cascade amplifier. Now in the three amplifier structures, the short circuit transconductance is same for all the amplifiers. It's the GM of this device here, it's the GM of this device, and the GM of this device here. It's the same if I'm assuming I've biased all the devices with same currents. So if all the GMs are same, then the short circuit transconductance is same. But if you see, the output resistance is different for all the three stages. In the first case, it is R0. In the second case, it's 1 by GM, approximately 1 by GM. In the third case, it's going to be GM into R0 square. So the gain into bandwidth product, the DC gain, if you see, the DC gain in the first example is GM R0. In the second example, it is GM R0 by 1 plus GM R0. I'll approximate this to 1. In the third case, the DC gain will be GM R0 the whole square. So if you see, compared to common source, the cascade's DC gain is GM R0 times higher. Now compared to common source, the common drain's DC gain is GM R0 times lower. But if you look at the bandwidth of a common source amplifier is 1 by R0 CL. In case of a common drain, it's going to be GM upon CL. Now if you notice here, the bandwidth of a common source amplifier is GM R0 times lower. DC gain is GM R0 times higher compared to common drain, but the bandwidth is lower. So here itself we can directly see this gain bandwidth trade-off. And when we talk about cascade, the R0 is going to be GM R0 square, which is GM R0 times larger than the R0 of a common source. So the DC gain is GM R0 times larger, and the pole is given by 1 by GM R0 into R0 into CL. So the pole is 1 by GM R0 times lower. So therefore, the gain into bandwidth product for all these three amplifiers will just be GM by CL itself. But the DC gains and the bandwidths are different for all the three amplifiers. But the gain into bandwidth product is the same. So I took a familiar example to show that we have already discussed this in the previous lectures. So this is not something new for us, that we can extend the bandwidth. So if you see, among the three amplifiers, common drain amplifier has the highest bandwidth, but it also has the lowest gain. So we are trading gain for bandwidth, and this is something we were already aware of. Now we'll look at, from a frequency domain point of view, and time domain point of view, what is this gain bandwidth product represent? What does it signify? To understand that, first I'll look at the time domain response. Now to understand the time domain response, all I need to do is just feed a sudden step input and see how the output responds to that. Now this is first I'm going to understand it's a simple single pole system with a DC gain A0 and study its response, and after that we will study the closed loop system. So if I feed a step input to the system, it's a first order system. The steady state value will be A0 into delta V, that's your steady state value, and the transient response will be this times 1 minus E upon T by tau, or T into omega P. So the output will raise asymptotically and eventually, it will raise exponentially, and eventually it will reach, it will try to catch up with the steady state value A0 into delta V in the steady state at T equal to infinity. Now this function has a maximum slope at the origin. So if you differentiate this, you can directly see you will get A0 into delta V times omega P into e power minus T into omega P, so e power minus omega P T. So you can see that the slope, this is the derivative of this function, is maximum at t equal to 0. After that, this value will always be less than 1. And the maximum slope occurs at the origin. So it looks, the slope will be maximum at origin, and after that the slope will reduce, and in the steady state the slope will become 0. Now if you see this expression here, what I get here, the maximum slope is simply a0 into delta v into omega p. Now this product a0 into omega p is simply gain bandwidth product. So gain bandwidth product in time domain, it tells me for a first order system the maximum slope with which the output can rise for a step input. So it's a measure of the speed of an amplifier, how fast the amplifier can respond to sudden changes. This is for a single pole system in open loop. Now what happens in a closed loop? To understand the behavior in closed loop, of course I can derive a direct expression. We already know it's ACL upon 1 plus S by omega CL. This is the closed loop response. And from this, we can directly write the slope is going to be ACL into omega CL into delta V. I'm going to feed a step input of magnitude delta V. I have written the closed loop transfer function. We have already derived it for a single pole system. We said it's the DC gain times the pole into delta V. That's your maximum slope. And this term is simply GBW, A times delta V. So we can see the maximum speed with which it responds for sudden changes will be similar for open loop and the closed loop systems. So that's what GBW tells us. Since the GBW is same for both, the maximum slope with which they will raise will also be the same. And that should make intuitive sense, because what's happening here is that when I am applying a sudden step input, that's like applying, I've already discussed, you can look at a step input as a sine wave of infinite frequency at t equal to 0. You can look at it like a sine wave of infinite frequency. I've already discussed in the previous lectures why is that. I said if you take a sine wave, the slope at origin of a sine wave is given by is proportional to the frequency of the sine wave. So let omega naught be the frequency of the sine wave, then it's given by A amplitude of the sine wave times the frequency. For a step input, it looks like the slope at this point is infinity, so that at this point I can treat it like a sine wave, but the amplitude is finite. So I can treat it as a sine wave with an amplitude of whatever this steady state value is and a frequency of infinity. So there is a sudden change, so it's like an infinite frequency sine wave. At infinite frequencies, we know that the forward path gain is nearly 0. It's negligibly small. Since the forward path gain itself is small, multiplied by beta, it's going to be even smaller. So which means if the signal is being fed here, the quantity which is being fed back is so feeble that I can ignore the feedback path and assume that the signal is directly traversing through an open loop amplifier. So that's why even though there is feedback, it's of no use, because the loop gain is so small, A beta is so small, that A by 1 plus A beta becomes so small that this approximates A of S itself. So that's why for sudden inputs, if you observe the output of your closed loop, or a negative feedback amplifier, it will look very similar to an open loop or a forward path amplifier. So to further elaborate on that, so what I've shown here, this is the open loop and closed loop frequency responses. The open loop response at very high frequencies can be written as A0 by 1 plus S by omega p, which is at very high frequencies, which means S is much greater than omega p. You can approximate it to omega p into A0 by S, which is nothing but GBW by S. Okay, so which is the gain bandwidth product by S. So it looks like an integrator. An integrator is a system with one pole, a pole at DC, and it's a system of this type, some constant by S. So this system is what we refer to as an integrator. At very high frequencies, it looks like an integrator, and the constant of integration is simply equal to the gain into bandwidth product. Now, if A0 is much greater than 1, if A0 is much greater than 1, the frequency, the product GBW also happens to be the frequency at which the gain becomes equal to 1. So all I have to do is that if A0 is much greater than 1 and you are at a frequency much greater than omega p, we can approximate the transfer function to omega p A0 by S. If I equate this to 1, I get the value of S or omega. I'm going to call it U, which is the frequency at which the open loop gain becomes equal to 1, or I'm calling it as the unity gain frequency. Omega U is given by A0 into omega p, or gain bandwidth product. Similarly, in a closed loop system, when you derive the transfer function for a closed loop system at very high frequencies, I've written the transfer function here. So at very high frequencies, I can ignore 1. This will again approximately be equal to omega u by S. I'm calling this term A0 into omega p, which is gain bandwidth product, as omega u. So it will be equal to omega u by S. So the frequency response at very high frequencies, when I say very high, the frequencies are much greater than omega p into 1 plus A0 beta and omega p. At those frequencies, the frequency response is indistinguishable between an open loop and a closed loop amplifier, because at these frequencies the gain is much less than 1. Because the gain is less than 1, A beta will also be much less than 1. Therefore, it looks like there is no negative feedback itself, and the frequency response of an open loop and a closed loop system will overlap at these frequencies. So that's why the maximum slope and the high frequency response were identical for closed loop and open loop systems. So that's it.